Good morning, everyone. Have you ever wondered how old the trees are at the school? I have, and I wanted to take you along with me today to do an experiment, to do some serious math, to try and figure out how old the trees are. Now, there are a couple of ways that people in the past, or people still do, to figure out how old trees are. The first method is to cut it down. Now, every year, a tree will grow a new ring. Now, let me put some pictures up to show you what I mean by a new ring. So as you can see from those pictures, right, there was a centerpiece, and then there are all these rings going out. And you've probably seen that if you've looked at a tree stump. Now, every year, a tree will add a ring. But depending on the climate and the weather right near a tree, if it's really sunny, but there's lots of good water and nutrients in the soil, a tree might grow faster. Whereas if a tree's living in a place that's pretty cold, there's not a lot of rainfall, there's not a lot of sun, there's maybe not a lot of nutrients in the soil, the tree's going to grow a lot slower. So you could have two trees, both of them are 50 years old, but one could be like way bigger than the other one just because it lives in favorable conditions. So what people will do is they'll cut the tree and they'll count the rings. Now, some of the rings have big gaps in between them, and that means, oh, the tree grew so much that year. And some trees, the rings don't have very big gaps at all, and that means the tree didn't grow that much that year. So you can see if the gaps are big, it's probably that tree that's growing really fast in those favorable conditions, those good conditions. Whereas if it doesn't have a big gap between the rings, you can tell it's probably that tree that's not growing so fast, and it's probably not in favorable conditions. So you can't really tell how old a tree is by looking at it. So like I was saying, one of the ways is for people to cut it and count the rings. But if you cut it to count the rings, then your tree is dead, and it is no longer going to add rings. So that seems like kind of a waste of a tree, right? Another way that scientists will figure out how old a tree is to use this, it's kind of like a large drill, and I'll insert some pictures in just a moment, and it's called a corer, and it's a hollow drill that goes deep into the center of the tree, and they pull out this chunk and put it on their little table, and they go, okay, that's the center of the tree, that's the outside of the tree. 1, 2, 3, 4, 5, and they'll start counting the rings that way. So it still hurts the tree, but it doesn't kill the tree, which is kind of a little bit better. Now, for our purposes today, to figure out how old some of the trees are on our school grounds, we are not going to be cutting down trees, and we are not going to be coring them. We are going to be measuring them and then doing some serious math. So, if you are in second grade or older, you're probably going to be used to the general idea of multiplying or dividing. But if you're younger than that, that's totally fine that you haven't learned that yet. You're getting a little bit of a head start. So the first thing we're going to do is take the circumference. Now the circumference is going to be like if I were giving the tree a big round hug. I'm going to touch my fingertips to the other side. Now some trees are obviously bigger than that. So I want to measure the full outside of the tree. So it's like a big circle, right? I'm going to take the circumference and I'm going to divide it. Ooh, third graders' ears might be perking up. Divide it by a silly number called pi. Now pi looks like this. It's actually a Greek letter, but we use it in math, and it stands for 3.1415. And then the numbers keep going for basically ever. So it's about 3. We're going to take that circumference, divide it by pi, and we're going to get something called the diameter. So you can see that this is a circumference, The diameter is going to be going from one point all the way to the other point, the opposite side in a circle. That's a diameter. Now the diameter is going to help us figure out how old it is. But now let's think about this. We might have a couple of first graders. One first grader is very short and the other first grader is very tall. Does that mean that the taller first grader is older than the smaller first grader? No, right? They're both in first grade. They just grow at different rates. The same thing happens with trees. Different kinds of trees will grow at different rates. So in any given climate, let's say it's sunny, there's water, and there's good nutrients, even though it's great favorable conditions, the trees are still going to grow at different rates because they're all individuals. Just like humans, if we were to feed those two first graders the same amount of food, the same exact food, they'd still grow at different rates because they're different than each other, and that's totally fine. But we have to take that into account when we're doing our math and when we're trying to figure out how old these trees are going to be, okay? So each tree has what is called a growth factor. Now the growth factor is this special number that scientists have somehow come up with, and I don't know how they did it, and I will not get into it. But basically it's this number that tells us, oh, this tree grows really fast, this tree grows really slow, but guess what? They might be the same age. So we're going to take that diameter, bloop, and we're going to then multiply it by that growth factor, that special growing number. Now that final number, our big equal sign, what we're going to get at the very end, is going to be a estimate, a guess, maybe this is around the age. So it's not going to be as accurate as counting those rings, but we're going to get a pretty general age. So if it said 53, we would know that our tree is about 50 years old. Could be 60, could be 40, but we know it's about 50, right? So we're never going to get the exact number. Okay, so we're going to do the math, and then we're going to chart it, and we're going to figure out how old a lot of our trees are, which is really fun. Now, one of the things I want us to do before we get to that, here are the instructions. I want you to think about the different trees at our school. I'm thinking. Okay, there's the redwoods right behind room 9. There's the eucalyptuses up by the 7 circles. There's the sycamore when you walk into the 7. There's all these trees, right? Try and think, which ones do you think are the oldest? Which ones do you think are the youngest? Is that oak tree up by the compost bin, the compost piles in the 7 circles, older or younger than the eucalyptus trees by the 7 circles? My hypothesis, or my educated guess, is that the oak tree is older than the eucalyptus trees, even though the eucalyptus trees are much bigger. I think the oak tree is older. So pause the video and take a minute to think about what your hypotheses are, what your guesses are. Okay, so really quick before we go, here is the growth factor chart. I will also send this along with a video in a separate file, so if you guys want to do this at home or want to do this as a class, the chart shows you the growth factor numbers and gives you a description at the bottom. Okay, so you're probably gonna definitely need a partner, and you're going to need a measuring tape, and you're going to need some form of string. And here's my partner. Okay, this is Mr. Warren. So we're gonna start with this American sycamore tree behind us. It's just right at the front of the 7 circles. So we're gonna put the measuring tape down for a moment. And I'm going to, now this tree isn't so wide I could do this one myself, but as you get to wider trees, you're going to need a partner. So if you're just doing dinky little ones, will be fine by yourself. So I'm gonna hand my partner one end, and I'm going to instruct my partner to just hold it against the tree. Now you don't want to start at the bottom, you want to start maybe 4.5-ish feet up. So we're at a pretty decent height. And then you're going to wrap it all around. Okay, let go. And then you're going to mark with your fingers, or you can mark with a pen, or you can cut the piece of string to kind of tell you how long. And remember, this measurement here is going to be that circumference, that measurement that goes all the way around. All right, so I'm going to show you a time lapse of us just measuring the trees. But before we do that, this is the most important part. You have to write down your data, your information. Data is just another word for information. So if I have this, it means nothing to me, right? So I have to measure it and then write it down. Say sycamore tree, however many inches, okay? I have my partner here. We've stretched out the piece of twine and that was where it ended. And we laid out the measuring tape, and look, it looks like it's probably about 47. So 47 inches, you want to measure in inches. And then we're gonna go write that down on our little notebook. Okay, so as you just saw, we measured a couple of the trees in and around the Seven Circles garden. Now, just to reiterate really quick, we're going to take that number, that circumference in inches. We're going to divide it by pi. So if you're using a calculator, your calculator might not have this on it, but phone calculators do. If you turn it to the side, it'll have pi on it. That's what it looks like. And you're going to get your diameter. That's going to equal d, diameter. Once we get that diameter, we're going to multiply that by the growth factor. Remember that chart? So, some of the trees have growth factors. I still am going to try and find one for the eucalyptus because eucalyptus actually grows really fast. So I would expect it to have a high growth factor. All right, let's do one together. And then I'll just crunch all the numbers and share them with you in just a moment. So let's start with that sycamore tree, which is that first one that you saw, the one right when you walk in the Seven Circles garden. The number was 47. So 47 inches divided by pi equals 14.96. Okay, 14.96. Now the sycamore has a growth factor of 4, which means I need to take 14.96 times 4. And I get 59.8. 59.8, and if we round that, which equals 60, so that tree is about 50 to 60 years old. That's pretty awesome. Now, just as a reminder, we measured them about 4.5 feet up the tree. So if you measure at the base, that can throw off your numbers. If you measure at the top, that's going to throw off your numbers because the stuff at the top is youngest because it just grew. So you're kind of measuring right about 4.5 feet, and that's going to give you your best estimate. So our sycamore we know is about 59.8 years. That's pretty cool. All right, let me crunch some more numbers and I'll share those with you. So all of our math is done and fun information for you. So let's recall really quick. We measured the big oak tree at the very top of the garden by the compost pile, like the big one with the branch that goes down that you can kind of like walk on. That large oak, the largest oak that we have, is estimated to be 183. Oh, so old. Then we had the sycamore, which was right at the front of the garden. And that one is estimated to be about 60 years old. Remember, that's the one we did together. Now, I was just thinking before I let my brain run off, if you don't have a calculator with the actual pi symbol, you can just remember to use 3.14, and that'll give you a pretty close enough answer. All right, then we measured that ash tree by the unicorn, and that one was estimated to be 108. Then we did one of the ashes, another ash tree by the bench area on the playground with the stage, by the stage, and we did the one that has the little piece of chain with a little hook on the end of it. And that one was estimated to be 74. Then the eucalyptus was estimated to be 75. So really kind of similar range here. We got a 183, 60, 108, 74, 75. So most of those trees are in the 60 to 80 range. And then two of them are pretty decently old. Now, of course, these numbers could be wrong in some way if these growth factors take into account the average growth, but we have sprinklers and we have really wonderful rich soil in the gardens, and the one on the playground is not going to be receiving as much nutrients from the ground because it's covered in asphalt, right? So you kind of have to take these things into account. Now, I want to look at our numbers here and see if your hypothesis, if you came up with one that involved some of the trees we had, or my hypothesis was correct. So my hypothesis originally was that the large oak tree was older than the eucalyptus tree, even though the eucalyptus tree is like massive. So the thing with eucalyptuses, I know, and this is part of my educated guess, is I know that they grow really fast compared to other trees. And it turns out, it looks like the eucalyptus, or the large oak, is like 3 times older than the eucalyptus tree. So it's like over 100 years older than that eucalyptus tree, which is really cool, even though they're about the same circumference at 102 inches for the eucalyptus and 115 for that oak. Really interesting. So one can be 183 years old and be the same size as the other one that's 75. Super cool. It was also really interesting to see that the sycamore was 60 years old. So the Seven Circles garden didn't used to be a garden. It's only been a garden for about 10 years. And as a kid, when I went to the school, that garden was just a hillside with grass. And I don't remember the sycamore being so large. And now, obviously, a lot of time has passed since I was in first grade playing kick the can on that hillside. But it's really interesting to know that, oh, that tree's 60 now. Happy birthday. That's fantastic. So I hope that you guys will try to do some of this either with your teachers as like a fun math project, or do this at home with your parents. I will include the growth factor chart and the instructions along with this video so that you can do it on your own. And if you do happen to measure any trees at the school that I didn't measure, I would love for you to send me an email with your findings, with your data, to garden@mayhairschools.org. That way we can start putting all of our data or our information into a chart so we can start tracking it and understanding the age of our trees.
So really quick before I really let you go, I always have so many thoughts. One last thing I want to just quickly touch on, and I'd love for you to spend even just 1 minute contemplating this idea, or longer, that's always fine too, that if that tree, that one big oak tree by the compost with that really low branch that you guys love to climb on, if that tree is 183 years old, then how should we treat that tree? Now, my first instinct is to say, well, we've got to treat it with reverence and love and respect. And that's true, right? That's so true. But it also makes me think, well, just because that tree is 183, what about the 2-year-old tree? We have to treat that one with love and respect too. But I think knowing how old a tree is really kind of puts that all into this nice, neat little bow on a box. It puts it into perspective where at first I'm like, protect the tree at all costs, right? That tree is so important. And it is. But so are all the other trees. Just because one is 183 doesn't necessarily make it more important than that 2-year-old tree. So when you're in the garden, or when you're out in the world, or where you're touching trees, we've got to be really respectful and find that love and that awe and that inspiration and that respect for the things around us, the living things, the beings, the beautiful trees around us. And in that respect, I think our whole planet will do some serious healing if we all bring that respect and share that love and appreciation for nature.